How's it going, everyone? Welcome to Chapter 3 of our text. So as I was going through last night and this morning, the material of Chapter 3, what I found was that the way that the material is ordered in its introduction is a bit confusing to me. Particularly in Chapter 3, what we're going to be doing is expanding our modeling analysis from statics of particles to statics of rigid bodies. And basically what that is going to allow us to do is to describe the tendency of forces to induce rotation. And since we're in statics, more particularly, the ability of support structures to oppose that rotation. However, what we're going to find is that in order to do that, we have to introduce this concept known as a moment. And the way that we compute a moment formally is in terms of a vector product or a cross product. However, it's easier to build your own intuition about the way that moments work using what's known as the scalar formulation. And if you just want to go build some intuition right now, go to a door that you can open and close and push it to open it all the way as far away as you can from the hinges, and then do it at the midway point. And what you will find is if you apply the same force in both cases, generally speaking, when you push on farther away from the hinges, you're going to tend to induce more rotation than if you push closer. Or if you've ever tried to loosen maybe a rusty bolt using a wrench and it didn't work, and what do? You go and get a bigger wrench. You're essentially extending that moment arm or that perpendicular distance, which also contributes to the tendency of a force to induce rotation. So a lot of stuff going on there, but I think it's easier to build up your understanding using the scalar formulation first, rather than going immediately to the vector formulation. So what I decided to do is just to basically wrap new video content, Module 0 and the last module that I recorded in this lecture, around the content that's organized according to your old textbook, which actually introduces, not your old textbook, but the textbook that we used to use in the course, which introduces the scalar formulation of moments first. So before we go on, let's kind of just talk about some general introductory concepts, a lot of which I've already alluded to. So we've been doing modeling of rigid bodies upon which forces act using what's known as a particle model. And remember, the reason that we're doing that, if you think back to the original lectures in the course, is from a statics point of view, we want to compute the quantities that we want, or estimates of the quantities that we want, as quickly as possible. This is a back of the envelope type analysis. It's not finite element method. So really what we're looking for is simplicity in our analysis techniques. And particle analysis is about as simple as you can get. Because if you think about all the examples that you've done so far, if you've drawn any free body diagrams by hand, you've collapsed basically these three-dimensional structures that exist in the real world to a single point with respect to modeling. And the reason that you could do that is that all the forces acting upon that body, if you looked at their lines of actions, they all pass through a single point. And in that case, what is known as a concurrent force system, what happens is all of those forces aren't going to tend to induce any rotation. They're only in aggregate going to tend to translate or move the body. So that allows you to treat the actual analysis using a particle model. However, generally speaking, when you have forces acting upon a body, you do need to consider the physical dimensions of the body, which cause you to incorporate the points at which the force is applied. And if you think about what I was just describing with the door, that kind of hits to that analogy. Whether you're pushing a force with a door, with 5 pounds of force at the midpoint of the door, measured with respect to the hinges, or all the way out, that's going to have a tendency to induce motion in different ways. So we need to capture the points of application of those forces, which is equivalent to capturing the geometry of the body itself. So that's what we're going to be moving to now, is how we actually analyze what are known as rigid body systems. And like a lot of things in engineering, what we're going to be trying to do is develop a way in which if we have a bunch of forces and a bunch of these things called moments or couples, and we'll distinguish those all in this chapter, that are acting on a body, that are tending to move it and rotate it, how can we replace the effect of all of those things by a very simple system consisting of only a force and a couple? So that's really our motivating goal in this chapter. Now, in order to do that, as you see with the bullets taken here from the text, we're going to have to compute a moment of a force about a point. And that's going to require us to introduce the concept of a vector product. So that's one of the things we're going to be doing in the modules. In addition, once we have computed the moment of a force about a point, we'll need to kind of specify that or move away from the generalization to computing the tendency, the moment of a force about an axis, which just describes how much a force tends to cause rotation about an axis. And then we'll move to this idea of a couple here in a minute. If you have something in front of you, like maybe a piece of paper, sit it down in front of you and push it one way, a certain amount, and push it in the opposite way, the same amount on the other edge. So this is hard to show you, but basically up here and down here. And what you're going to find is that combination of forces purely induces rotation, because what's going on is the tendency of this force to push it up is offset by the tendency of this force to push it down. So there's no translation. That totally rotates the body, and that introduces what is known as a couple. So what we're going to find is that any system of forces acting on a rigid body, again, can be replaced by an equivalent force, which describes a tendency to move it, and an equivalent couple, which describes the tendency to rotate it. One concept that's really important, not necessarily from solving problems, but with respect to understanding why we draw free body diagrams the way we do, is understanding the differences between external and internal forces. And really the differences depend upon how you're actually setting up the free body diagram of your problem, which, as we've talked about a lot up until now, depends upon what forces you're trying to solve. So if we were interested in maybe determining the amount that these individuals have to pull on the rope in order to move the truck, which is equivalent to calculating the tension in this rope, right? From the perspective of us, this entire truck is a rigid body, even though it's clearly an assembly of multiple things, like its wheels and the cabin and all of these. I'm not a trucker, so I'm going to mess up some of the terminology. But the key point is, even though this is composed of components, we're going to just kind of model it and bundle it together as a single rigid body. And anything acting upon that entire body is referred to as an external force. So clearly, the force that we're applying by pulling on the cable is an external force. Clearly, the tendency of the road to induce those reaction forces that oppose gravity and keep it from falling through the actual road, those reactions, R1 and R2, are external forces. And the weight of the actual aggregate combination of the truck itself is an external force, because that's exerted on it by the Earth, right? That's described by Newton's law of gravity, which we previously went over. So even though there are going to be internal forces that keep everything together, right, they keep the wheel attached to the axle and keep the axle attached to the frame of the truck and so on. From a modeling point of view, we only need to consider what's ever going on at the external interface of that actual rigid body. Another thing that we need to talk about is this idea of the principle of transmissibility, which is going to be something that's going to come up a lot in this chapter. And the idea is, if you have a force acting upon a rigid body, remember that all forces have line of actions. If you were to move that force anywhere along that line of action, what you're going to find is that the tendency of that force to induce motion on the body is the same. So you can slide, if it's easy from your computational point of view, forces along their line of actions and do your analysis with any equivalent force along that line. Hopefully that makes sense. Sometimes you got to see it in an example to understand what I'm saying. So in this particular case, from the point of view of actually moving the truck, right? If you pull it from the front, or that's pulling it from the front, or push it from the back with the same amount of force, even though the internal stresses that result at the points of connection, like clearly if you're actually pushing on the bumper, right, versus pulling on the actual front bumper, the internal forces inside that system are going to differ. But from a motion point of view of the entire rigid body of the truck, the resulting tendency to induce motion is going to be the same. And the reason that these are called equivalent forces is, if you think about it, that line of action, this force, F and then F prime, are just slid along it in both circumstances. So if I draw that line of action here, I can slide this force anywhere along that line of action, including all the way to the back, and apply the force on the bumper. And from the perspective of the rigid body of the truck, I get the same tendency to induce motion. So hopefully that made sense, and you do not want to watch that with me. I do want you to watch it, but not with me, of course. And what we're going to actually find here is that the key points of this lecture are: make sure you know the principle of transmissibility, what that means, the general concept that I had of external and internal forces, along with how we're moving away from a particle model, which is only valid for concurrent force systems, where all the lines of actions pass through a point, to that of a rigid body model, which is also going to allow us to describe motion. But most importantly, I hope that you realize that all the modules 1 through, let me get the actual last module here. Sorry, my mouse is not working very well. It's got too much latency here, but we'll use the keyboard. That always works. So everything through module 6 is going to be from the old textbook. So don't get confused with any references to particular pages or chapters or example problems. It's going to give you all of the content that you need in order to understand how to compute the moment of a force about an axis, various example problems, and so on. And then what we'll do is, in the second part of this lecture for the week, we will actually discuss the example problems from your homework, which I will get up today. And I am going to have an issue ending this video because of this mouse thing, so apologies in advance. I do know how to use a computer. It's just, I'm sure many of you have ran into this, particularly if you use a low-end computer like we were given from Alamo, that you sometimes get latency with the mouse. So enjoy the videos, part 1 through part 6, and I will see you again in real time in Module 7, where we'll discuss just a couple concepts that are in Chapter 3 of your textbook that weren't in the old lecture material that I posted in the middle.